Yes, ID number 155. Are you there? 156.
Yes, sir.
Okay. 157.
Yes, sir.
158.
Yes, sir.
Okay. 159.
Yes, sir.
160.
Yes, sir.
161.
Yes, sir.
Okay. By the way, what is the last ID number in this section? Is it 169 or 170 or anything beyond that? Okay, probably that's not your problem.
I think 170, sir.
170. Okay. Thank you. Right, I think we can get started. Attendance is abysmally low. Maybe we'll wait for a minute or two. Meanwhile, are there any doubts with respect to eigenvectors, eigenvalues, matrix diagonalization, invariant subspaces, anything for that matter?
Sir, where do we have to submit this project report?
On Moodle. Okay, so I'll set up a link so that you can submit your project reports. I think the submission deadline is 6th of December, 6 p.m. if I'm not mistaken. And remember, you'll have to submit one project report for the entire group. Okay, so you don't have to submit individually. Any one group member should be able to submit. That should be enough. Similar to how you submit your scribe notes, there will be a submission link for your project report as well on Moodle. And similarly, there will be a link on Google Classroom for section B, not for section A.
Sir, we have to submit only PDF, right? Of
Only
report.
PDF. Only PDF.
And should we follow that format given for scribes?
Yes, you should follow the same format that you followed for scribes, for scribe notes. Okay, and at least section A students, please ensure you write it in LaTeX. And if I sort of catch hold of somebody who has not written the notes in LaTeX, I'll just give a 0 for project report.
Excuse me, sir.
Yes?
If you would give us an idea about the hard limit on number of pages.
There is no hard limit. You feel free to write as much as you want as far as it is relevant.
Okay, thank you.
And if you still want to know a little bit more, would sort of say that keep in mind your own classmates when you are writing your project report. Okay. So each group is given one project topic, not all project topics, right? So if you're writing your own project topic, write it so that your own classmates should be able to understand what's happening.
Okay, got it.
Okay, right. That's the general guideline for all project reports. As far as page limit, there is no page limit. And of course, I'm not expecting you to submit a book, right? So yeah, I think that much is enough as far as guideline is concerned. Any other questions? Okay, so then let's get started. We have a lot of material to cover. So, right, so this is something new today. We're going to begin with a new module in this course. Inner products and norms. Okay, so as of now, we only have a vector space structure with us. Okay, what does that mean? That means we have a set on which we have two binary operations, and with a field, all of these four things satisfy your vector space axioms. Okay, but now we want to sort of bring in a little bit of geometry here. Okay, in the sense that we should be able to measure lengths and angles between vectors, but not only for specific vector spaces like R2, R3, in which we already know how to define lengths and angles. Okay, we now want to do this for any vector space structure. Okay, so it could be, for example, square integrable energy functions that you study in signals and systems. It could be set of infinitely long sequences that also forms a vector space. So for such vector spaces, and of course also including R2, R3, C2, C3, etc., etc., how do we define length and angles of vectors and between vectors respectively in an arbitrary vector space? Okay, that is the topic for today. Okay, now R2, I'm sure all of you know what this is, right? And you've seen this before as well. This notation, I'm not sure whether you've seen it or not. Okay, so these two vertical lines and these two vertical lines is the notation for length. All right. Apart from the notation, I'm sure all of you know what this is. Right? What is this called? Square root x square plus y square. What is this called?
Distance from origin. Magnitude.
Magnitude. Okay, distance from origin. And also length of vector xy in R2. Okay, remember, as we have emphasized this earlier as well, whenever we say vector and you imagine it as if it's an arrow, the tail of the arrow must be at the origin. Okay, so distance from origin of the point xy is the same as length of the vector xy. Okay, but this specific way of defining length is what is called the Euclidean length. Or instead of length, a more mathematically appropriate word is norm. Okay, so this is what is called the Euclidean norm of the vector xy in R2. So far I think that should be fine. Now the question is this the only way in which I can define length? Or are there other ways of defining length of the same vector? So would anybody want to comment on this question?
Sir, what do we mean by length over here?
Exactly. That's a very good question, but it's like a chicken and an egg problem. I'm trying to define what is a length, but I'm trying to appeal to your intuition of length. Okay, so if your question is more mathematical, then please hold on for another slide. If not, then length is what we colloquially mean by length, right? Our day-to-day use of the word length. So in that sense, in our day-to-day terminology, right, is there any other way to define length? So yeah, for example, Gandhinagar city, it's a good example. we have these rectangular grids. I don't know how many of you are familiar with the way Gandhinagar is structured. There are these rectangular grids of roads. Okay, and I can take a fancy example. I think New York City also has roads that are laid down in a proper grid-like format. Okay, so all of these are sort of buildings, or as far as Gandhinagar is concerned, sectors. And for now, assume you cannot go inside these sectors. And say you are at this position, which is your origin, and your destination is this point xy. Right, so distance is basically length considered from the origin, right? So, or sorry, length is distance considered from origin. So what would be the length of this vector?
Same x square plus y square under root.
Yes, sir.
Same. Why? You sort
From
of
Pythagoras theorem.
agreed. But if you sort of think about it physically, right, and you're supposed to go from point 0, 0 to point xy, and length, as I said, is sort of connected or is exactly the distance between these 2 points. Right? As far as the first point is origin, I hope all of you agree that distance is length. So in that sense, would the length of this vector or distance between the origin and the point xy be equal to square root of x square plus y square?
X
If
plus
we
y.
cons-
So I think since two of you spoke at the same time, I couldn't hear any one of you. So what would be the length of xy in this case?
if we consider the case of restricting only to the roads, then it will be x plus y.
Is it x plus y or something more? I mean, x could in principle be negative, right?
Absolute value of x plus absolute value of y.
Right. Right. So can I sort of say that the length of this vector xy is absolute x plus absolute y? Yes or no? Similarly, let's say, or extreme example would be, consider that this sphere is modeling the surface of the earth. Okay, here you have your north pole and the south pole. What would be the length of this vector?
2 times radius of
Pi r.
2 times radius. That is 1. Anything else?
Pi r.
Pi r. So, are any of these wrong?
no.
And is only one of these right? Out of the same question, put it in another way. So depending on the circumstance, all of these answers are right, isn't it? But then that makes us think, when if these two numbers are correct, can't I have more than these two numbers? For example, if I am computing the distance in kilometers, I would have one number. Simple thing is, if I compute the same distance in meters, the number would be much larger. So as far as the number is concerned, you can have infinitely many different numbers that give you the length of the same vector. Okay, and then so scaling is just one thing, but there are different ways of looking at length, right? As these two examples demonstrate. Okay, so first, my hope is you see that there is no unique way of defining length of a vector. Right? Another way, you may say it is practically useless, but what stops me from defining length in this way? Right? So it's because of this Euclidean definition of length being hardwired into us, right from our school days, that perhaps it is a little difficult to accept that this is just one way of defining length out of the infinitely many possibilities. Right? But again, more than anything, I hope that you see from these examples this idea that the definition of length does not have to be unique. Have I convinced you, or are you still skeptical about this? Do you accept that there can be more than one way of defining length?
Yes,
Yes,
sir.
sir.
Okay.
So then we can define a length as means we can find any path that leads from that point to the destination point. The length of that path will be the distance.
So once again, be careful. I'm not saying length of any path is the distance. So don't get confused between length of a path and length of a vector. So for example, if you look at this definition, right, there would possibly be no path, right, with this length taking us from point 0, 0 to point xy. Agree?
Yes, sir.
So distance is something that I just used as a tool to show you the possibility that you can have a different way of defining length. Okay, but in principle, length does not have to depend completely on distance. Right? But I think you're going in the right direction. I think what you want to ask then is, if there are multiple ways of defining length, right? And length is just a number, right? So basically length boils down to a function. Let's call it for now, or if I use the same notation here, these two pairs of vertical lines, then length as of now seems to be any arbitrary function that takes in one argument from your vector space V and gives you some real number R. Right? Whether it is, for example, this, whether it is this, or whether it is this. All of them seem to be functions of the same kind, right? A function that takes in an argument, basically a vector from your vector space V, and gives you a real number. So then the question that we are encountered with is any such function from V to R a length? Or are there some conditions that these so-called length functions should satisfy in order to sort of intuitively satisfy our definition of length? Agree?
Yes, sir.
So, for example, can I say that this is length? Is this function defining length? That it's also a function that takes a vector and gives you a real number. Can I say this gives me length of xy?
No, sir.
So length should
Why?
be positive.
Should be positive, right? When we say length is -2, sort of does not satisfy our intuition about length. Okay, so therefore, we may require that any function that we call a norm or length should not be negative. Okay, it can, of course, be 0, right? If I take the origin and I ask what is the length of origin, right? I mean, 0 seems to be a natural answer. So 0, not a problem. Negative, that should be eliminated. Okay, so similarly, there are some such intuitions about the notion of length that we impose as conditions on functions that are allowed to be called a length. Okay, so let's look at those conditions. And whenever you have a vector space over which there is a valid function that is going to satisfy whatever conditions that you are going to see next, then that vector space is called a normed vector space. Okay, a vector space with a norm. Before we look at the conditions, there is one requirement that we ask from the vector space. The requirement is that the vector space has to be defined over the field R or C. No other field is allowed. Okay, so make that point clear. A vector space on which you want to define a concept of length, okay, that vector space has to be a vector space over the field which is either real numbers or complex numbers, nothing else.
But sir, I have a doubt. Like means it's fault of function definition that it will length will less than 0. So why we are restricting on vector space? Means for
No,
any
no, no.
vector space we can get length. No?
No, so that's what I'm trying to say. So your question is about the field, right? Why are we putting this restriction on the field?
No, means why are we putting means for any vector space we can get length? No, because length will always be positive. So why there is need to define some new vector space named norm vector space?
No, I'm not defining a new vector space. I'm saying you have a vector space over which these two binary operations are defined, right? Plus and scalar multiplication. Right, now let's take this example of R2 itself, the previous one. Here. So this is a length on R2, right?
Yes.
Now look at this. On R2, as a vector space, you have the element-wise vector addition and element-wise scalar multiplication with real numbers. using these two operations, can you define this operation? Remember, this plus is not your vector addition plus.
It's a function definition.
Yes.
Then we can define.
No, but we need to define the function, right? Using only your basic vector space operations, this is undefined. You cannot perform this given an xy using your vector space operation and get this number, right?
No.
You need more tools.
Yes.
Okay, which is why we are saying that we need the definition of norm.
Okay, sir.
Is that clear?
Yes, sir.
Okay. Okay, so right, maybe I forgot to mention this. Using these two binary operations, it is not going to be possible to define length. Why? What is the nature of these two operations? So the binary operations, right, both of them are binary operations, whereas length, we should be able to define length of every vector, right? So length in principle should be a unary operator. Okay, so the nature of your vector space operations are not going to satisfy the definition of length. You may say, what if both the arguments for your binary operations are taken to be the same? Okay, but in that case, you remember, I hope, that the vector addition operation gives you a vector and not a real number. Okay, so that cannot be used for defining length. Similarly, scalar multiplication, it in fact uses two arguments, both arguments coming from different sets. So you cannot set both arguments to be the same. And even if you do that, the resultant is still going to be a vector rather than a real number. There is no way that you are going to be able to use these two binary operations to define length, because intuitively length should be a real number. Clear? That
Yes,
is
sir.
why we need more tools defined on the vector space. Right? And once again, I'll repeat this. A vector space has to be defined over the field of R or C. Only then we can define length on it. So let's now look at the conditions that we impose on this function from V to R in order to be called a norm. First one, as we just discussed, no matter what your vector is, this function that we are going to use in order to define length of any vector using this function cannot be negative, as we just discussed. Okay, that I hope is clear. The second condition states that the length of any vector, if I say is 0, then that particular vector has to be the additive identity alone. Okay. Similarly, if I find the length of theta or the 0 vector or the additive identity vector, whatever definition you are using for length of this vector has to be 0. That cannot change. Again, this is mathematically encoding our intuition that if I start at this point and don't move anywhere, then I have not traveled at all. Okay, so the length has to be 0 of the origin, and the only vector whose length is 0 has to be the origin. Right? So do take note of this if and only if condition. Okay. Both of these conditions taken together are what are called positive and definite. Okay, so this definition that we just assumed, you can see that this will satisfy these conditions, right? The next condition is, so let's say again, going to appeal to your intuition of R2. So length of this vector and the length of this vector and the length of this vector. How should the lengths be related? So let's call the original vector drawn in white by V. Let us say the vector drawn in red is some, I don't know, A scalar multiple of B, and length of this blue vector is minus B times V, where A and B both are greater than 0. What should be the lengths of the red and blue vector relative to the length of the white vector?
So it should be A times the length of B of
The
red
length
vector.
of A times B should be A times B, the
A
length
times
of B, right?
Yes.
And
for
what about
it should be
length
B times length of B.
B times length of B? So in other words, what we are saying is the length of a scalar multiple of the vector V should be
mod A times length of V.
mod A times length of V. Do you see, because of these two conditions, why, I mean, these two conditions imply that the field that we have assumed are either R or C.
But sir, if field is C,
Mhm.
then this operation means that is A dot V, length of A dot V is equal to mod of A dot length of V. So
Mhm.
here, sir, if A belongs to C, then in right hand side,
Right?
magnitude of A will be magnitude of that complex number.
Yes. So that is
So sir,
absolute
if
value of A.
A,
It's not magnitude, okay? It's the absolute value of A. So
yes,
in other words,
absolute means
right.
that is,
Any complex number A can be written as R E I theta.
yes.
Then absolute A would be R.
So sir, in this definition of length,
Mhm.
if we have two complex
So
numbers, then
just
they
a
can
minute,
also
just a
give.
minute, Vandan. I'll interrupt you. This is not a definition of length. This is a condition that we are imposing on the functions that can be length.
Okay, sir.
Right. Yes. Go ahead and ask your question.
So, sir, if we consider vector space over real numbers, over real number of fields, then
Right.
this means this second condition implies a uniqueness of that number or uniqueness of that scalar multiplication. But in case of
No, for
complex numbers,
example,
there is no.
no. So A and minus A, right? These are two different scalars. Right? Even if you put a restriction that A should be a real number, but A and minus A would be two different scalars, isn't it?
Yes, sir.
But they would still affect the length in the same way. In complex number fields, of course, there are infinitely many complex numbers with the same absolute value.
Okay, sir. So here we cannot say that A is means some unique.
Yeah, not at all.
Okay, sir.
Okay, so this property is what is called absolute homogeneity. For any vector x in your vector space A and for any scalar from your field, remember when I write field from now onwards, as far as non-vector space is concerned, you should understand the field to be either R or C. Okay, so that is why there is no problem in this, right? Otherwise, for any other field, for example, polynomials or sorry, rational polynomials, you will have to define this. Okay, but A is either R or C, and therefore this is well defined. Right? More importantly, it sort of fits our intuition. That's the second condition. Third condition, it encodes our intuition that let's say I want to travel from, I don't know, Gandhinagar to Ahmedabad. Right? So the vector starting at Gandhinagar, assume your Gandhinagar is origin. Right? So your vector from Gandhinagar to Ahmedabad, there would be certain length of this vector. Similarly, there will be a vector from Gandhinagar to, let's say, Baroda. And similarly, a vector from Baroda to Ahmedabad. Okay, what can you say about length of the vector from Gandhinagar to Ahmedabad vis-a-vis the length of the vectors from Gandhinagar to Ahmedabad and Ahmedabad to Baroda? I'm basically talking about this situation.
The vector addition.
Right, so V is U plus T, but how about the length of V and the relation between length of U and
So the triangle triangle
Exactly.
inequalities. That is
And
length
the
of
length,
V is more than length of U plus length of V is less than length of U plus length of W.
is necessarily less than
Equal
Less
to
than or equal
also
to.
everything.
less than or equal to. So that is again our general intuition that if you deviate from the straight path, you are always going to travel at least as much as you would travel on the straight path. Okay, so that is what is called triangular inequality. Okay, so in the previous demonstration, V was nothing but U plus W. Okay, so the norm or the length of the vector x plus y must be less than equal to the norm of vector x plus the norm of vector y. Is it clear? Does it make sense?
Yes.
Okay, so these are the three conditions that we require a function to satisfy for it to be called a norm. Now onwards, I'm going to replace the word length by the word norm. Okay, so maybe for a day or two, just keep that in mind. Then I'm sure you'll also get used to it. Okay, so any function from V to R that satisfies these three properties is called a norm, and a vector space with a valid norm is called a norm vector space. And the notation for a non-vector space will be as this tuple. Okay. Also note that once we have the notion of norm, we can define the notion of distance. Okay, on a vector space which has a norm, using the norm, we can define distance between two vectors x and y simply by defining the distance between x and y as the norm of the vector x minus y. Okay, and similar to, instead of using the word length, we are going to use the word norm. Similarly, instead of using the word distance, more mathematically appropriate word is metric. Okay, so you get a definition of distance for free. Right, I hope that makes sense again. Okay, let's look at examples of non-vector space quickly. On Rn, right? This is basically what we also looked at in the previous example. Here, R2, we had this. In Rn, it becomes this. Okay, this is again a norm that is frequently encountered in a lot of engineering applications. Because of its popularity, right? Has a name by itself. Okay, this is called the one norm on Rn, and it will be denoted by the subscript 1. Find the Euclidean norm is what all of you are familiar with. Let me write it here for the sake of completeness. This will be summation I going from 1 to n xi squared squared. This is denoted, or this is also called the 2 norm. And now I hope you see why this is called 1 norm. This is called 2 norm because of this power and this power. Okay, and the notation for Euclidean norm is this. Okay, subscript becomes 2. I think I will leave it as an exercise for you to check that the 1 norm satisfies all the 3 properties that were listed above. Let me give you more example. We also have what is called the max norm or the sup norm on Rn. That is defined simply as the maximum of the absolute values of each coordinate. Okay, this also has its own notation. Again, I think it is easy to verify that this definition or this function also satisfies the 3 properties that were listed in the previous slide. Something which is closer to signal-then systems. Let's take the vector space of polynomials of degree at most n. And each polynomial is going to be considered as a function on the interval -1 to 1. Okay, so that also forms a vector space. And we are going to assume real coefficients. So this forms a vector space over R. You can define a norm on this space as this definition suggests. This is what is called the capital L2 norm. And I hope you recall this from your signals and systems course. Right? What is this? Forget polynomials. X is a continuous time signal. So what does this mean? Square root of the energy
Square root of energy.
of the signal X. Okay, that also is a valid definition of norm. More example? No. Okay, I'll give you one more example. Yes.
Why are we make it constraint of -1 to 1?
There's no particular reason. I don't want to write P, I mean from minus or Pn on R, simply because then I have to define this a little bit carefully. Right? Because for example, the constant polynomial, this, what will happen to this? This is in fact
Infinity, it goes to infinity.
exactly right. Can the norm be infinity? See, in signals and systems, you may have, I hope, heard everyone talking about finite energy signals. Yes or
Yes,
no?
sir.
Why? It's exactly this reason. You can see if I take polynomials over R, you have several, in fact, most of the polynomials will have an infinite norm. Can we have an infinite norm?
No, sir.
Why? What would happen to this property?
Not defined.
It will not be valid, right?
Yes, sir.
Because if I pick A to be 0, right, 0 into x on the left hand side is theta, right? Norm of theta from first positive definiteness is 0. So the left hand side is 0. What about the right hand side? 0
0
into
to infinity.
which is not defined. Okay, so you can see, sir, most of the mysteries in signal systems are there due to vector spaces. Right, so that is why in signals and systems we usually stick with finite energy signals. Okay.
So, sir, capital L2 norm is for this constraint -1 to 1
No. You can define it over R also, but not on polynomials. See, when you say finite energy signals, if finite energy signals don't contain polynomials, right?
They
Yes.
contain decaying exponentials.
Exactly. And you see why they have to decay, because if they don't decay, then the energy goes to infinity.
Yes, sir. I am just asking that the L2 norm, the name L2 norm is for
Because of this,
constraint
and
-1 to 1 interval or for
no. For any interval.
Okay, sir.
This L stands for, has anybody heard this? Stands for the name of a mathematician, French mathematician, Lebesgue. I shouldn't go into more details of this because I'll have to. The way this integral is defined is not the usual integration. Okay. And I'm not going to go into more of that. As far as your functions are continuous, the Lebesgue integral is the same integral that you are aware of, but as soon as your functions become nasty, I'm not even going to define what do I mean by nasty. In that case, you cannot use your usual definition of integral, and you will have to redefine or generalize the definition of integral. And one generalized definition of integral is what is called the Lebesgue integral, which is what is used over here. So whenever I say this integral, whenever you see this integral in the L2 norm, just keep it in a corner of your mind that this is not necessarily the usual integral. But if the function that you are trying to integrate is continuous, then it is your usual integral. Okay, so that is why the name L2. Okay, I think I'm running out of time. I won't give you more examples, but even in your case of discrete signals, you may have seen the definition of energy, right? Instead of integral, you have a summation. So that also forms a norm. Okay. Okay. So apart from, as we started out in the class today, we wanted to define length, and I hope you have a rough idea now of what do we mean by length mathematically. Okay. He also said we wanted to define angles between vectors. Okay. So for that, again, your vector space does not have enough tools. Okay. Again, remember, vector space means only two binary operations. None of the two binary operations give you scalars. Angles, again, intuitively should mean scalars. So in order to define angles between vectors, we need additional tools, and the tool that is going to be used is what is called an inner product. I don't know how many of you are familiar with inner product, but I am certain that all of you are familiar with the term dot product. Yes?
Yes.
Yes, sir.
Right. So inner product is just a generalization of dot product. Okay, and we are going, and I'm sure you already know, once you have dot product between vectors, you can define angles, right? Why? Because cos of theta between two vectors v1 and v2 is
Dot product of vectors divided by their ends.
divided by what?
Product of their magnitude.
Product of their
Norms.
No.
norms, right? Now you sort of see that you have already seen norms earlier. Okay, so if you look at this particular relation, right, you have the definition of norms, but you do not have the definition of inner products. Once you have that, in principle, you can define angles. Okay, so inner products is just one way to, or the way basically, to define dot products on any arbitrary vector space. But again, similar to the case of norms, we are going to assume that the vector space is defined over the field, which is either R or C. On such a vector space, an inner product is any function or mapping that takes two arguments, both from the vector space, and gives you an element of the field. Okay, so this can be slightly unintuitive in the sense that if my field of the vector space is the set of complex numbers, this inner product can give me a complex number. That happens, then we cannot use this relation over here. Okay, but as far as your vector space is a vector space over R, your inner product is always going to give you a real number. The notation for the inner product is this: two angular brackets. You will have the first argument here, the second argument there. Okay, and this also has to satisfy certain properties. First property, similar to your norms, is called positive definiteness. It says that if both arguments, right, are the same. Okay, so if I try to find the inner product of x with itself, what happens over here? You should end up with a real number. Okay, moreover, that real number cannot be negative. Right? It's sort of saying I'm trying to find the angle between a vector and itself. Okay, so these two are perfectly aligned with each other. And the inner product should not be, I mean, first of all, it should be a real number, irrespective of whether the field is R or C. And then that real number also cannot be negative. Okay, it comes from this intuition. Right? If V1 is equal to V2, what would V1 dot V2 be? Be nothing but length of V1 into length of V2. So cos of theta.
Norm square.
norm squared, and that would cancel out, right?
Yes.
Right. So norm squared, norm is positive, norm squared also must be positive, or at least non-negative. So because of that intuition is sort of saying that no matter what your inner product definition is, but if I plug in the same argument in both places, I should get a non-negative real number. And because I'm going to get norm squared, this norm squared, if it is 0, then the x that I have used must be theta. And similarly, if I use x as theta, then the inner product of theta with itself must be 0. Okay, so that's the first condition.
But sir, if we are finding angle of a vector with itself, then it must be equal to 0. How?
Yes, but you see the dot product. Is dot product directly giving you the angle?
No, sir.
No, it's giving cos of that angle, right?
Yes, sir.
Right. So inner product, as I said, is a generalization of dot product. Using inner products, indirectly you can find the angles, not directly.
Okay, sir.
Okay, the other condition that this function has to satisfy is that in the first argument, the inner product must be linear. Okay, so for all x, y, z vectors in V and for all scalars a, b coming from the field, remember the field is either R or C. Inner product of ax plus by with the vector z must be equal to a times inner product of x with z plus b times inner product y with z. Okay, this also comes from the intuition of your dot product. If I have two vectors in R2 and I do a linear combination of that, so the inner product of these two vectors independently with the third vector and the inner product of the linear combination with the third vector will satisfy this definition. Now, if the inner product must be linear in the first argument, what about the second argument? Should it be linear or not linear? So we say that the inner product is not symmetric, but it must be conjugate symmetric. Okay, which means that if I interchange the first and second argument, the inner product becomes the complex conjugate of the inner product of the two arguments in the first order. Okay, as far as your field is real, okay, if f is real, then the inner product of y with x is of course equal to the inner product of x with y. Okay. If f is not real, then this of course is not true. So any function therefore that satisfies these three conditions is what is called an inner product. And a vector space V, remember the field must be R or C, with a valid inner product is what is called an inner product space. And the inner product space is denoted by V with the inner product. So let's look at examples. This again is nothing but your dot product. I hope you recall this. Summation xi yi. If I write x and y as column matrices, then in short I can write this simply as x transpose y. Right? I hope all of you are familiar with this inner product or dot product basically.
Yes, sir.
Okay. And once again, I think it should be easy to see that this particular definition of inner product satisfies the three properties. For example, x with x, what would that be? X transpose x, which is summation xi squared. Right? This, of course, we know is greater than equal to 0 and is equal to 0 if and only if all xi's are 0. Similarly, linearity, simply because matrix multiplication is linear, right? So this will be linear in the first argument. The field is R, so this is also conjugate symmetric or simply symmetric. Let's look at Cn. This is a slightly interesting case. So in Cn, what happens if I use the same definition of inner product that was there on Rn? Why can't I define the inner product on Cn in this way?
Conjugate symmetry rule will not hold.
And will it not hold? Why not? How about, so conjugate symmetry you're saying will not hold?
Yes, sir.
Okay, and anything else? How about positivity? X inner product X would be? Can you say this is non-negative?
No, sir, it will be
Sir,
complex.
it will be complex number, so we can.
Exactly. So this also is not satisfied. Basically, you can see the problem is xi squared may be a complex number. Okay, so the way out is to define it in this way. Okay, x inner product y is summation xi yi complex conjugate. So even if y is equal to x, what will happen? Xi into xi complex conjugate is
Absolute value of x.
xi squared. Then this surely is non-negative.
Sir, here yi bar denotes the complex conjugate of yi, right?
Yes, yi bar denotes complex conjugate of the number yi.
Okay, sir.
And once again, if I denote x as a column matrix, then I can write this by y star x instead of y transpose x. Okay, y star denotes not only the transpose of the column matrix y, but it denotes the complex conjugate of all components of the transpose of y, which in short is written as conjugate transpose. Okay. Let's look at another example. So once again, I'm sure you have seen this in your signals and systems course. Right? The integral, of course, in this case, I took the interval to be 0 to -1. There is nothing special about this. You could easily replace 0 by, let's say, -1 or 0, 1 by any a comma b. Doesn't really matter. Okay, so the integral of the pointwise product of these two polynomials. Okay, that also is a valid inner product, right? And you have used this, right, in your signals and systems course.
Convolution.
No, this is not convolution. So in your Fourier series, right, you must have shown this. I don't know, what was it? 0 to 2 pi some sine t into cos t dt. Right? You've done this in your signals and systems, isn't it? What do you get?
0.
0. Right? So this is nothing but your L2 inner product. But of course, not the L2 inner product on polynomials, but on periodic continuous time signals. Right?
Yes, sir.
But now I think if you understand what we are discussing here, then I hope you will have a better intuition about signals and systems. What we are trying to do is you're trying to understand the space of signals using geometry. Okay, remember, norm is a way to bring in lengths. Inner product is a way to bring in angles. So if you talk of signals, right, there is nothing geometric over there. But if you use these tools, right, if these tools are defined on your signal space, you can sort of imagine that there is a geometry in this set or space of all signals. Okay, and geometry is something that we all are hopefully, geometry is a tool that helps us imagine something, isn't it? Okay. This I think so. We should maybe leave this example for now. I'll just mention this example, and maybe in a year's time you will come across this. Have you studied probability and statistics?
Yes, sir.
Yes, sir.
Oh, you've already done that course.
No, sir. Course no.
Oh, okay. So that's what I meant. So you may not be familiar with random variables, right? So for
So
now,
that we know in communication course.
Acha. So you know what is a Gaussian random variable
Yes, sir.
Yes,
and a
Gaussian.
Gaussian random vector?
No, sir, that we don't.
Vector, no, don't know.
Okay. Then fine. Let's just leave this example for now.
Hello, sir.
Yes.
Can you please repeat why do we need the vector space? Sorry, why do we need the inner product on a vector space?
The inner product, if you look at this. Yeah. This particular relation, right, that all of us are familiar with as far as R2 and R3 are concerned, the same thing can be defined on any vector space. Now, in order to look at this relation, to sort of see that, we need to define this numerators in some way, v1 dot v2. But once we have a tool that allows us to define v1 dot v2, then the right hand side is defined, and therefore I can somehow figure out what are the angles between these two vectors v1 and v2, right?
Yes, sir. Yes, sir.
Right. So in that sense, what I'm trying to say is inner product is a tool that will help us visualize the vector space. You may say that what is there? I mean, R2, R3, we know how to visualize. But how about finite energy signals? How about periodic signals? Can you visualize that? At least for me, I think the answer would be no, because I don't know how to imagine functions as points. Okay, but once you sort of have this definition in place of an inner product, using inner products, you can sort of talk about angles between two vectors. If these two vectors are your signals, right, that sort of gives us some way to imagine at least these two vectors, right? You may not be able to imagine the entire signal space simply because it is infinite dimensional. Okay, but this is a tool that brings in geometry. That, I mean, once you have geometry, then it sort of opens up ways to imagine it.
Yes, sir. Yes, sir. And so it will be a function of angles, not the angle itself, right, sir?
Yes, yes. So that is what I'm saying. Inner product directly should not be interpreted as angles.
Okay,
And
sir.
in fact, if your vector space is a vector space over the field of complex numbers, I mean, you cannot even define angles using inner products, at least not any arbitrary angle. Okay, because the right hand side for complex numbers would be a complex number, right? And any complex number you cannot assume is cos of the some angle theta. Okay, so inner product in that sense is a generalization of the concept of dot product. Dot product is used as a way to get angles. Okay, but once your vector space is defined over the field of complex numbers, that also in some sense goes out of the window. But there is still something that you can get out of defining inner product, even if the vector space is complex valued. Okay?
Yes, sir. Yes, sir. Thank you, sir.
Right. One way is, if you have seen all these examples that we discussed in this slide, these seem to be very close to the definition of norm. Okay, and if you look at the first property, positive definiteness, this is basically norm. Right? So you can prove that if I have a vector space V with an inner product, so basically you have an inner product space, then I can define this function from E to R in this way using the definition of inner product. Right? Then you can show that this forms a valid norm. But since we have used the definition of inner product in order to define norm, this particular norm is what is called an induced norm. Okay, and once again, I will use this as an exercise for you guys to show that this induced norm is actually a norm, in the sense that it satisfies the conditions required for a function to be a norm. As far as interpretation of inner product is concerned, it will help you define this thing. Okay, so if you have an inner product space, two vectors x and y are said to be orthogonal if the inner product of x and y is 0. Okay, now I hope it sort of starts making sense. Right? We have talked about perpendicular vectors. We have used that right from our school days. We know that if two vectors are perpendicular in R2 or R3, their dot product goes to 0. Right? So we are just generalizing the same thing. Right? All we are saying is, since there is no single definition of dot product, okay, so given any inner product space, it will have its own definition of inner product. And two vectors in the vector space are orthogonal if, according to the definition of inner product, the inner product of these two vectors x and y turns out to be 0. Okay, so what I mean by this is, let's say you have the vector space R2. right? But on this vector space, there is nothing unique about the inner product. You can have more than one definition of inner product. So let's just denote two different inner products as subscript 1 and subscript 2. It may happen that there are some vectors xy in R2 such that x inner product y according to the first definition is 0, but x inner product y for the same x and y using the second inner product, this may not be 0. Okay, this can happen. Okay, so what is orthogonal or perpendicular? It really depends on how you are defining angles. Okay, and again, remember, the inner product is just a tool to generalize the definition of angles. So if you accept that there are multiple ways of defining lengths and distances, then you should be able to accept that there are multiple ways of defining angles. And orthogonality is something you have, I'm sure, heard as far as signals and systems is concerned, right? Sine and cos are orthogonal. Why? Because according to the L2 inner product, sine and cos are orthogonal. Okay, so you can sort of imagine sine as, let's say, the y-axis, cos as the x-axis, because of how the inner product enables us to imagine them. Let me just finish with a few more definitions and then I'll stop. Two vectors are said to be orthogonal if their inner product is 0, but they are said to be orthonormal if, apart from being orthogonal, the length of these vectors is equal to 1. And when I say lengths in an inner product space, right, this always means the induced norm.
Sir, even if field is complex, norm of both should be 1.
Norm, remember, irrespective of the field, norm is a function from V to R, not from V to F.
Yes, sir.
It again comes from our intuition that length should be a real number and not a complex number. Okay, so we have defined orthogonal, two vectors being orthogonal. You can also define a set of vectors v1 to vn to be orthogonal. So set of vectors v1 to vn is orthogonal if any two distinct vectors from this set have their inner product to be 0. Okay, and similarly orthonormal if, apart from being orthogonal, all vectors in that set are unit vectors. Then, if a set of orthonormal vectors also forms a basis of the given vector space, we say that the basis is an orthonormal basis. Okay, so quick example of an orthonormal basis, let's say of R2. Your
1, 0, 0, 1.
right, the unit vectors in the x and y axis. Okay, so that would be an orthonormal basis. But remember, once again, basis by definition doesn't have to be orthogonal, as we have seen earlier. Okay, in fact, in order to talk of orthogonality or orthonormality, you will need an inner product space, not just a vector space.
And sir, also it is not necessary that all orthonormal are basis.
Yes, of course. If they don't span the vector space, then it's not a basis. Okay. Another important term that you will hear quite frequently is an orthogonal matrix. Okay, so a matrix A, whether it has to be a square matrix, but otherwise it can contain real numbers or complex numbers. This square matrix is said to be orthogonal if, remember, there is a possibility of slight confusion here, if all its n columns are orthonormal. Okay, we are defining an orthogonal matrix, but the definition of the orthogonal matrix relies on the n columns being not just orthogonal but orthonormal. Okay, why? Because once this happens, you can see that A star A, where A star denotes the conjugate transpose, A star A becomes just the identity matrix. Right? If your columns are only orthogonal but not orthonormal, A star A will be a diagonal matrix, but the diagonal entries would be different from one. Okay, but how do we interpret this? A star A becomes identity. That simply means A star, the conjugate transpose of the matrix A, is nothing but its inverse. Okay, so for example, whenever you have a linear system of equations to solve, if the matrix A is orthogonal, you can see that solution is very easy to obtain because the inverse of that matrix is already almost given to you. You don't have to do any computations to compute A inverse. Okay, so that is one importance of orthogonal matrices apart from several others. Yeah, I think we'll stop here. I've already taken more time than I should have. So this is where we'll stop for today. I thought if I could finish this entire set of slides, then I would need only one lecture more, but as it seems to me, that's not going to happen. So we will have to most likely meet next Friday as well. Right. So thank you.
Sir, if entries of orthogonal matrices are 1 and -1, then they are called Hadamard matrix, right?
So Hadamard matrices are examples of orthogonal matrices. But are you saying that any orthogonal matrix that contains only ones and minus ones are Hadamard matrices?
Yes, sir.
In fact, so Hadamard matrices contains the square root n, isn't it? Right? A matrix that contains all ones and minus one in principle can never be orthogonal.
Yes, sir. There means A star A will be some n times
N times
identity.
identity. So at least
So,
by definition, it is not orthogonal.
okay, sir.
And the same is true. I don't know, you may have come across discrete Fourier transform. So that also is close to being orthogonal, not exactly orthogonal.
Hello, sir.
Yes, Taran.
Sir, here for a vector to be orthonormal, the norm its norm should be one, so the norm should always be the induced norm.
Yes, yes, that is mandatory. Whenever we
Sir,
talk of orthonormality, the unit vector definition should use the induced norm only.
means we cannot define any other norm.
No, you can define any other norm, but for the vectors to be orthonormal, you must use the induced norm only.
Oh, okay, sir. Okay, sir.
Any other questions?